Hi, and welcome to Craig the Geologist, After Dark. After Dark. Well, the lights are turned off because our topic today requires dimly lit conditions and a good UV flashlight. Today we're talking about the science of fluorescence and phosphorescence. That means we get to talk about one of my favorite and possibly the sexiest subject there is, quantum mechanics. Quantum mechanics. Fluorescent minerals seem to be interesting to pretty much everyone, and you can see why. You shine a light that you can't see with your naked eyes on a rock in the dark, and it glows bright colors, greens and oranges, reds and yellows, depending on the minerals. And I don't know, perhaps it just activates our monkey brains. We like bright, shiny objects, and when you're in a dark room and something's glowing at you, you are just immediately attracted to it. One of the most popular pastimes in my area, in the Great Lakes region, is going out at night and looking for Uper lights. I've got a selection of those right over here that light up a beautiful, bright orange color. And there's a lot of other things on our shores that light up in the Great Lakes region as well. Fossils, calcite, even slag glass. There's a lot of very beautiful stuff on our shores and on the land, because what's on the shores is the same as what's on the land when you go out at night and shine a light on it. But why is that? What's happening when we shine a UV light on a mineral to make it fluoresce? So let's talk about that a little bit. Let's start with talking about fluorescence. Now, I should begin with the word about the quantum mechanics we're about to discuss today, because I am not a physicist, I am a geologist, but I do have an intense interest in quantum mechanics. I have studied it about as intensely as a casual scientist who doesn't actually study it can. And a lot of what I'm going to demonstrate up on this board is not literally what's happening in the quantum world down at those scales, because what's happening at those scales cannot be translated up to the macro world. You can't really visualize what's happening. And I've talked to a lot of physicists before I finally came to this realization that you just can't wrap your head around what electrons are doing, what they look like, because they don't look like anything, at least nothing that our minds can perceive. They're these fuzzy wavelengths, and they're basically mathematical equations just floating around. It's pretty much impossible to draw a physical parallel that makes sense in our world. These quantum wave functions that exist and don't exist in various places at the same time. It's all insanity. So what we do is we show things that are false, things that aren't literally true, but will help you to visualize what's happening in a world that you can't visualize. All right? Does that make some sense? Hopefully it makes some sense. So let's talk about fluorescence a little bit, and let's draw a model of an atom that scientists rejected more than 100 years ago. But we're going to draw it anyways because it's going to help us visualize what's happening. In the center of your atom, you have the nucleus. This will be our nucleus, full of protons and electrons, or not electrons, but protons and neutrons. I'm going to draw little ends in here for neutral. And around it, you have these electrons orbiting. Now, we do still talk about electron orbitals and such, but they're not literally orbiting like planets around a star. But we can visualize it because electrons occupy positions that we still call orbitals. that correspond to the amount of energy they have. The electrons in the outer orbitals have more energy than the electrons in the inner orbitals. And so you have orbitals that we can visualize extending outward around the nucleus of the atom. Well, this is totally off center, but we're gonna fly with it, all right? So if you have a fluorescent material, what's happening is that a photon, which is a packet of light energy, doesn't have to be visible light. It can be ultraviolet light, could be radio, microwave, could be anything in the electromagnetic spectrum. But a packet of energy, a photon, strikes the atom and knocks an electron to a higher orbital. That is, the photon hits the electron, is absorbed into it, and pushes that electron from here to there. The electron's energy is quantized. That's where the term quantum mechanics comes from. That is, it has the energy of either 2 or 3. It can't be 2.5 or 2.4. There is no, it's either one or the other. And so when the electron gets struck by that photon, it absorbs the photon and it jumps up one level, one orbital. And it sits there for a moment and then comes right back. When it comes back into the empty orbital space, it releases a photon of its own. That photon is what we perceive as visible light in fluorescence. So, for example, if I shine this UV light on a piece of cyanite with fluorescent soda light in it, a UPER light, as people around here call them, you can see it glowing a bright, beautiful orange color. What's happening there is that the UV light is striking an electron. Well, striking a lot of electrons, but we're just going to use one atom as an example. Striking an electron, causing that electron to have too much energy and to jump up one orbital level. And then it comes back down and releases a photon of energy. The photon has the exact same energy as the difference between this one and this one here. So if, let's give them random made up numbers. If this orbital has energy of 6 and this orbital has energy of 10, then the photon that comes shooting off of it has an energy of 4. All right, so when it jumped from the 10 level orbital down to the 6, releases a 4. And that energy level of the photon corresponds directly to the wavelength of the light. That is, it corresponds directly to the color of light that you see. And so what happens is UV light bombards the electrons, they jump up an orbital level, and when they come back down, the color of light you see corresponds exactly to the energy difference between the different orbitals that the electron passed through. It's pretty complex, and yet kind of simple the more you think about it. I find it incredibly interesting. And so you get different colors on different materials. So you can see that it's not always electrons jumping the same distance. It depends on the atom. It depends on the type of mineral that it's in. If we talk about phosphorescence, what we have is fluorescence with a delay. That is, photons are striking the electrons, causing them to jump, and then they come back, but they don't come back right away. Maybe they wait 1 second or a half second or a minute or 3 minutes. Your classic children's glow-in-the-dark toys are phosphorescent. So if we do a quick comparison here, we could take this piece of Upper light here, shine the light on it. You see that beautiful glow on there. You turn it off and the glow stops immediately. On the other hand, if we take some toys from my children's bedroom, these are little decorations that can go up. We shine our UV light on these and we turn it off. They continue to glow. And that's the difference between fluorescence and phosphorescence. Fluorescence happens in real time and stops the moment you take the light off. Phosphorescence, your electrons have jumped energy levels, same as they do in fluorescence, but they don't come back right away. They come back gradually. And eventually all the electrons will come back. You know, this stuff doesn't glow forever. It eventually goes dark. But that's the way phosphorescence and fluorescence work. Got a whole range of colors here. Let's get these guys all lit up. And there you go. We do, of course, get phosphorescence in rocks and minerals. Otherwise, I wouldn't be talking about it. Here I'm shining a UV light on some Petoskey stones, which in my area are often phosphorescent, which is something a lot of people don't realize. So shine that bright UV light on it, turn it off, and there's still some remnant glow. You can see it for a few seconds with your eyes, for about 1 second with the camera. Now you might be asking yourself, why does fluorescence require a UV light? If it just involves a photon striking an atom, couldn't it happen with visible light or with radio waves or any other type of electromagnetic photon? You know, microwaves, radio, gamma, ultraviolet, infrared. They're all just different wavelengths of the same electromagnetic energy. What makes a UV light so special? Well, first let's point out that not all UV light is made the same. Minerals will fluoresce under one particular wavelength of UV light, but not another. UV covers a broad spectrum just like visible light does. Visible light goes from red to blue with your yellows and greens and oranges in between. UV light covers a spectrum as well. Most of the minerals we look for use long wave ultraviolet light. For Upper light hunting, we use a very specific wavelength, 365 nanometers. Easy to remember. It's fun to go hunting for Upper light 365 days out of the year. You want a 365 nanometer UV light. And I'll talk more about the lights you use for Upper light huntings in a later video. But the wavelength of the UV light matters because not all fluorescent minerals will fluoresce under a long wave UV light. Some require a mid-range UV light. Some require short wave UV. It just so happens that the Upper lights we look for require long wave, and that's very handy because long wave UV lights are far cheaper than short wave UV lights. And the mid-range ones, you got to order from specialty shops. You know, a good long wave UV light, like a flashlight like this, will run you somewhere in the range of $30 to $60, while a good short wave UV light will typically cost you $300 or $400. So I don't even have a short wave UV light. I'd like to one day, but I'm not really, you know, obsessed with fluorescent minerals like some people are, and I don't want to be. I feel like I could be, and that's a path I don't want to go down because it becomes people's whole personalities if they're not careful about it. Our monkey brains are easily hijacked by shiny objects. What can I say? And so the wavelength matters. But where I was going with all this, though, wavelength matters because you can't just bombard an atom and electrons with a random wavelength of light and expect it to do what you want it to. These electrons are at specific energy levels, and so the photon that strikes it has to be at just the right energy itself to give that electron a push up to the higher orbital. If the wavelength is too large or too small, the photon will go right by it and leave it unaffected. Or it'll just be absorbed by the atom as a whole and make it warmer. It'll become heat energy. But in order to knock that electron up to a higher orbital, depending on the energy of the electron that's being knocked up, you need a specific energy of light coming in. And so for our UPR lights, it requires 365 nanometers. And it just so happens that for a lot of minerals, long range will do the trick and it'll knock that electron up for you. For phosphorescent minerals, very often visible light will push the electrons up. They're not quite so choosy. If I take out the children's phosphorescent toys and shine a regular flashlight on it and then turn out the light, of course it glows in the dark. But if you shine a UV light on it, it does a much better job. UV light tends to have a lot more energy in it than visible light. The smaller the wavelength of light, the more energy it has. It's a little bit backwards. You might think, oh, the bigger the wave, the more energy. But for electromagnetic energy, the smaller the wavelength, the more tightly packed in those waves are, the more energy you get in each little packet, in each photon. And so UV light is extremely energetic. It's also terrible for your eyes. Don't ever shine it in your eyes or near your eyes. A lot of people wear protective glasses when they're out UPR light hunting or doing anything with UV light. Long wave is less dangerous than short wave. And as long as you're not shining it in your eyes or on any reflective surface that's really shining a lot of UV back at you, you're going to be okay. You don't really need to worry about it much. Although that advice might change if you're really obsessed with fluorescent minerals and you're spending all night, every night playing with UV lights, then you might need to worry about your eyes a lot more. Now, it's worth noting that not all atoms, and of course not all minerals, fluoresce. There tend to be only a few varieties of atom when they're held in a certain configuration within a mineral that pulls the electrons into just the right energy level and position so that if they are struck by UV light, they will jump to a higher orbital and come back. And so, of course, you know, if you shine a UV light on any random surface, it's probably not going to fluoresce unless it's dusty. Because anybody who's ever used a UV light in their house will tell you the most brightly fluorescent stuff in your house is the dust that is all over. I don't get it. I don't know why that is, but it's just a fact. In fact, in this video, you'll probably see brightly fluorescent dust everywhere because I live in a dusty home. It's just the side effect of being a geologist. I live with a lot of rocks. It's going to get dusty. In fact, most minerals that are fluorescent are not naturally so. For example, calcite is often a fluorescent mineral. However, pure calcite does not fluoresce. It only fluoresces when it's doped by a few specific atoms. That is, doping is when a small amount of contaminant atom that wouldn't normally belong in that mineral make its way in and substitute for some other element in there. In sodalites, those fluorescent sodalites, bright orange, pure sodalite doesn't fluoresce. But if you get a little bit of, as I recall, sulfur in with the sodalite, then it begins fluorescing. Sulfur, pure sulfur by itself, I believe doesn't fluoresce. I don't think I have any pure sulfur to test with me. Well, I might in a drawer. But when sulfur is locked into a sodalite mineral, then the electrons are put into a position that they can absorb the UV energy and hop up to a higher orbital and then release it, and they create that beautiful glowing effect. Well, I hope you found that explanation helpful. Now, if you're disappointed I didn't spend more time talking about the specific minerals on my desk here, worry not. In upcoming videos, I will be talking about a couple of minerals at a time in depth, really going into the science of each one. And we'll really flesh this out and have some fun. In the meantime, thank you for joining me for this episode of Craig the Geologist After Dark. After Dark.